if you are having this relation, then at a temperature say beyond 45 degrees centigrade, the power generating capacity or the electricity generation from a PV panel is quite diminished, and which actually does not suffice our. Then what we look for? We look for some sort of cooling of the PV panel by circulating some sort of coolant on the back side and then extracting that heat. So ultimately you can see that the high grade energy, whatever is getting converted, gets the help of thermal energy or the low grade energy. So that's how I thought that it would be better to appreciate low grade energy or thermal energy and how it can be actually utilized for charging a system, how we can store it, and then whenever it is recalled for, how we can actually get that discharging. So basically, if I'm speaking about thermal energy storage, these are some of the classifications through which you can actually like go through when I'm speaking about what ways thermal energy storage can be classified. So one way is in terms of its physical storage terminology, and another one is through its chemical storage aspect. So when I'm speaking about the physical storage terminology, one is in terms of the increase in temperature or reduction of temperature, you can actually charge or discharge a thermal battery. Since it is a storage, so we can also, like electrical battery, we can name it, can point it, which is known as the thermal. So similarly, on the basis of that name of thermal battery, it can be classified as a variable temperature or sensible heat storage, and another one constant temperature type where there is a change of phase but the temperature remains constant, but it is an isothermal process through which we call it as a liquid storage system. Now, if I'm speaking about the chemical storage, basically we will be having this thermochemical energy storage, and then there is one more which is known as the sorption energy storage. Like it is say a surface phenomenon like adsorption system, or it can be a volumetric phenomenon where you will be having absorption taking place. So if it is more where you don't have any chemical like energy change, then it is known as a physisorption type of scenario. But if you are having certain part of the system where there will be the breakage of bonds and then releasing the energy, or joining of bonds and then storing the energy, then it is known as chemisorption. So that way this classification of chemical storage comes, one as the sorption one and another one is the thermochemical storage. Thermochemical storage is nothing like suppose you are having say lime, and you are mixing water to it. So once lime and water are mixed, it is an exothermic reaction, and it gives out energy in terms of the enthalpy. So that's how whatever energy is stored in the lime, you are actually generating the energy and utilizing it. So basically the Le Chatelier principle is to be called for, because there the reversibility of the reaction will be there, and you can see that how the energy can be stored once it is the exothermic reaction, and how the reaction can help us to release the energy when it is an exothermic reaction, and how it can be helping us to store the energy when it is an endothermic reaction. Everything gets governed by the Le Chatelier principle, or again like you can say how the concentration will drive it as a forward reaction or backward. That's how you can conceptualize this thermochemical storage. In terms of maturity, like when we are speaking about the practical aspect, this is not at a very good technology readiness level. TRL level is quite good. Like the things where you will be having the say that scale. But this thermal energy storage in terms of sensible as well as for latent has been used for a long time. As I was telling, like if you are having say a bag of sand and you are exposing it to sun, the sand bag, because of its heat storage capacity, it will keep the heat. And that heat, if you want to pump it out, just put a pipe through it and a water circuit. That water will get heated and you can use the energy which is there in that bag of sand. So that is a very matured way of harnessing low grade or thermal energy when we are comparing it in terms of the storage. Now this is a bit of physics in it. If we go to second law of thermodynamics, we we know that the second law of thermodynamics says that energy transfer is not unidirectional. Of course, we all know that always energy passes, always energy gives its pattern a lower potential system from higher potential system. But second law of thermodynamics says that the reversible is also possible, but you have to do some work on the system. That's how the refrigerators, that's how the heat pump works. If I'm speaking about second law of thermodynamics, there is a concept which is known as dead state. What is that dead state? Dead state is that state when your system is at its minimum potential or minimum energy. Like it should be at say room temperature. It should not have any sort of activation energy in it, but still it is having some energy which you can't extract. So that is the dead state. Now, if I'm speaking about a system which is at a very high temperature from your room temperature, say 30 degrees centigrade or 25 degrees centigrade, the amount of energy which you can extract from that high temperature system will be much higher in comparison to the system which is much closer to the dead state. That's why if I'm speaking about thermal energy, I should always appreciate high temperature thermal energy storage system or high temperature latent heat thermal energy storage system, where by virtue of the phase change I will be storing the energy or releasing the energy, but all at a very high temperature which is much higher than the dead state or the normal temperature and pressure at which the system is there. So this actually helps us to appreciate one more concept which is known as the second law efficiency of a system. If a system is working at a very high temperature, then the second law efficiency of that system will be much higher in comparison to that of a system which is working very closer to dead state. So this is what we wanted to appreciate. We wanted to understand how we can use it. But like if I'm saying that I'm having a thermal battery which is say working at 200 degrees centigrade, which is say working at 500 degrees centigrade, then it is very big challenge how I can store the energy at how I can store the energy at that high temperature state. Then you should have insulation. You should have some system which does not allow the heat to come out of the system. Although it is challenging from that perspective, but if you want to appreciate the second law efficiency of that system, or sometimes it is also called the exergetic efficiency of the system, high temperature latent heat thermal energy storage systems are a better solution, and they can sometimes be compared with the electrical energy storage system or with those lithium ion batteries in which you are actually storing the. So one concept of understanding the terminology of energy storage is through energy density. So why we use lithium ion batteries? Lithium ion batteries are having very good energy density. The amount of energy which is stored per unit volume is much higher when you are storing electrical energy in lithium ion batteries. Similarly, this high temperature latent heat thermal energy storage, because of its capacity to store more energy at a higher temperature when it is much far from the dead state, always gives an advantage, and some way or the other you can say that it is at par with electrical energy storage when we are comparing. And how we can actually energize this high temperature thermal energy storage system. I already spoke about the PVT system. Like if you are having a photovoltaic system and if it is exposed to a temperature say 50 degrees centigrade somewhere in Churu in Rajasthan or very close to the border of India, there the temperature is quite high and the efficiency of the PV panel will be much lower. But if you are having some sort of cooling mechanism so that whatever heat is getting generated can be used for some other process related activity, that can be coupled with this latent heat thermal energy storage system, and your efficiency of the PV panel will be also nominal, and at the same time you will have a system which will be working in conjunction to the electricity generation for some other process related activity. So this is the way you have to appreciate when we are speaking about high temperature latent heat thermal energy storage system. Some more insight into it. So when I'm speaking about, for example, I started with steam being a magic fluid. So if you take water from ice till it reaches its vapor state, it is going through different phase change. But this phase change happens at constant temperature. Although the change of phase is happening, but the temperature remains constant, or it is an isothermal process. And that is the advantage where we have this high temperature thermal energy storage latent system with constant temperature to be a better solution in comparison to that of the sensible heat, because as I was mentioning about the energy density will be much higher in a latent heat thermal energy storage system in comparison to that of a sensible heat energy storage system. Sensible heat energy storage system is something which I just now mentioned. You take a bag of sand, expose it to sun, and whatever energy it is having in it, now you just run a pipe through it with water, and then whatever energy that bag of sand will have, you can just tap it and use it. So that is the one which comes through this process where the temperature is changing. But if I'm speaking about the latent heat energy storage system, this is the process where the temperature remains constant, but energy stored per unit volume is much comparable to what you are having in a storage system as that of a lithium. So that we have to share. There are challenges. The biggest challenge is how you contain the heat at such high temperature, because there will be heat loss. So you have to insulate the system. You have to make it isolated in a way that it does not come in contact with the external atmosphere. Somehow you can manage it, and it is a win-win situation. And remember, this is a low-grade energy. You are not converting it to electricity. So that way also, if I'm speaking about the techno-economics, is much in a better option when we are comparing it with the processed energy. So there are aspects which actually helps us to understand like from solid to vapor directly. So there are certain system which does not goes to the liquid state directly. From solid it gets converted into vapor. So if you take the vapor dome of water, there is something which is known as the critical point. So that point is that state where the liquid state directly gets converted to the vapor state. So sorry, the solid state directly gets converted to the vapor state without going through this phase transition of the liquid state. So that type of scenarios are to be appreciated when we are speaking about solid to vapor state. However, if I am speaking about solid change, for example, if you are speaking about say iron and carbon, like when we are having that metallurgical operation to make steel, so this iron and carbon, they go through various meta state in between where you get different allotropic behavior of the same metal. Although it will be in the solid state, you raise the temperature, but it will be having different allotropic form. That way also you can store energy. So that is also one way of understanding how a solid system can also help us to store energy. These are some of the aspects which you have to appreciate when you are speaking about the thermal energy storage system. One thing here I want to speak about as the phase change. That I gave the example of water as the phase change, because from solid ice it gets into liquid and then finally into water vapor. But the most simplest phase change material which a kid can also appreciate from childhood is wax. Like whatever we have, the candle wax, basically you know, like once you lit the candle and then the phase change happens, and then it gets converted from the solid to the liquid phase, and then I think now this phase change material or wax is having lot of applications when we are speaking about thermal wax. Like in many practical applications you can think of utilizing the wax. For example, if you want to reduce the temperature of this room during the scorchy summer of say the month of May, you can layer it out with an envelope of wax which will not allow the heat to come from outside to inside. It will just change its phase. So that way you will be arresting less heat, and the overall air conditioning load of this building will be minimized. So this is one aspect through which you can appreciate this a wax-based phase change material which can be utilized as a thermal energy storage. Of course, it is having many other problems associated with it. For example, if I say that I have to have a layer of wax on the roof, it can drip down and it can actually fall on the table in which you are doing your assignment. So those are some of the research areas which you can think of when you are utilizing wax to minimize the heat arresting in a particular control volume. And this comes as a package when you come up with a solution as a scientist to find pathways how to go ahead and do things about. Now wax is also having one more disadvantage in comparison to that of its heat storage capacity. I just now mentioned about a bag of sand to store the thermal energy and then utilize it. This is a sensible heat. What wax does, wax once you like expose it to some heated surface, it gets melted and that's how it store the energy. And once you again bring it with means colder environment, it gets solidified and this energy. So that's how the energy gets stored and energy gets released. But this is one aspect of wax where we appreciate something you would have heard about the specific heat of a particular substance. For example, if I'm speaking about water, water is having a specific heat of 4.2, more specifically 418 SI unit. So that's how it is. If you want to know how much a 2 kg of water at 50 degrees centigrade will store energy, so what you multiply it times that 4 times 50. So that will give you the total amount of energy which that 2 kg of water or 2 liter kg and liter for water or less does not matter. So that's how you get the specific. This wax, they have a very good specific heat. They have a very high storage heat storage capacity. The one advantage of this wax is, see, you don't have to store the energy. Actually you don't have to always store the energy. You have to also discharge it. So for discharging, it is not only the heat storage capacity, it is the heat releasing capacity or heat diffusivity. So there is one more terminology which is known as the thermal conductivity. So this heat storage capacity and thermal conductivity are the two competing criteria which each material should have so that it can behave as one of the best battery which you can design. Wax doesn't have that. Wax is actually having a very good heat storage capacity, but when it comes to the diffusivity or when it comes to the thermal conductivity, it is not. So then again, it is another research avenue, another thought process which you have to think from how we can make the system having a better diffusivity or what way I can enhance the heat transfer capability of wax. So again, it is a research avenue which you can think. And one more thing which I want to highlight about the wax is it is highly hydrophobic. Like if you just put it in water, you know it will not mix in water, which is not a very good thing. Suppose you want to mix it and utilize it in the building envelope, it will not mix itself with the cement, and that way the structural stability or the strength of the wall will increase. So this is also one more challenge where the hydrophobicity of phase change material is to be converted into hydrophilicity. How you make it water dispersing, how you make it more water miscible when it is compared to a crude wax which is not actually having this hydrophilicity. This is again one more research evidence. So you can see how many research evidence we can think of when we are speaking about the challenges associated with thermal storage system. So there are certain techniques through which we can do it. Sometimes we call it as the micro encapsulation, where we actually encapsulate the actual wax in a sheath which is more hydrophilic, and that way you can have the wax to have its heat storage capacity. And with this hydrophilic sheath or the shell which you are copolymeric shell which you are making, you are actually enhancing the overall accessibility of the wax, and you can mix it with concrete or you can make it a part of you can mix it with water to make a slurry and then exchange the heat from one to another. So that way you can You can think of how the hydrophobicity of wax can be converted to a miscible slurry or can be made more user friendly when it comes to its maximum utilization of the capacity of the system. Now, the selection of phase change material. There are many ways. One such way is the multi-attribute decision system, which is sometimes which is also known as the MADM process, and it's nothing. It is more like giving weightage to different attributes of a system, and then choose on the basis of ranking which which phase change material or which thermal energy storage system you have to decide. We'll not go into the details of it. This bit on the operation research or mathematical side of it, where you give ranking or where you give weightage to each of the properties which you have to decide upon to make the system more usable, to make the system more smarter by utilizing some mathematical which is known as an MADM or get into decision. That there are many other branches. One such technique is MADM is Topsis, which is mostly used by scientists. So that way in market you will be having n number of phase change material. Which one you want to pick for your utility? If you are trying to store energy in your house, so which phase change material you will use? So that time you have this algorithm and utilize it for picking the. So I will give you some case studies which we have done at IIT Delhi. So this is about a high temperature latent heat thermal energy storage system which can be coupled with supercritical CO2 based Brayton cycle. So supercritical CO2 is a magic fluid which is having the behavior of both liquid as well as gas. So one way it will be having less viscosity as that of a liquid, and at the same time it will be having high energy density. And one advantage of this supercritical CO2 state, supercritical carbon dioxide state is that it gets into its supercritical stage at a very low temperature, much closer to our room temperature. That's how you don't have to use lot of energy to change the state. As I was mentioning about the critical state, like when it changes from the solid state to the vapor state without going through the liquid state where the phase change material happens, the supercritical CO2 gets into its supercritical state at a very low temperature. Of course, you have to a higher pressure. So that way the total amount of energy which is required to convert this CO2 at its supercritical state is much lower, and that's how you can get maximum energy being utilized by using this supercritical CO2 in comparison to that of say air standard cycle for the Brayton cycle. So Brayton cycle is the air standard cycle which is used for power generation. You go to uh, uh, you go to any power plant, there are mainly two types of power generating system. One through Rankine cycle, which is through steam, and another one through air standard cycle, which is Brayton cycle. In Brayton cycle, if you are using SCO2, supercritical CO2, then in that case the efficiency of the system becomes much higher at the cost of spending less amount. So this CO2, how it can be coupled with a high temperature thermal factor, that is the study which we have done. So what we have taken silicon. Silicon example, more closer example of silicon is sand. So sand, you know sand what it is. You have seen every. So sand is actually melted at a very high temperature, some 1000+ degrees centigrade. So if you want to get the sand melted, so it should be melted at such a high temperature, and then you are actually charging and discharging the sand to store the energy. From where you will get such high energy. So to melt sand more than the 1000 degrees centigrade, it is around 1300 degrees centigrade, which is the melting point of sand. Where you will get that energy? That energy you will be getting, say, from solar, where you will be having some concentrated system like a parabolic dish collector which will be having the energy being focused at its focal point, and then you take it and then you utilize it for melting the sand. You take it from some waste heat. Suppose you are having a metallurgical operation in an iron and steel plant, then there also the metallurgical operation takes place at a very high temperature, say 1200 to 1500 degrees centigrade. So whatever waste heat you are getting generated in that scenario of metallurgical process of iron and steel, that can also be taken and used as waste heat recovery and utilized for melting the sand. So that way, what you are doing, you are not actually using a fossil to energize or melt your sand. You are using some sort of renewable or some sort of waste heat to energize it. But the advantage is whatever I just mentioned, that at a higher temperature, the second law efficiency of the system will be much higher in comparison to when it is closer to the dead state. This we wanted to speak about when we started this we started this experiment related thermal energy storage of silica, and we did a simple thermohydraulics study of an exchange material. This is more from the computational transfer point of view, where you take a battery, you mesh it, you make it a small control volumes, you impose the boundary conditions. There are many boundary conditions which you can impose, more realistic to more idealistic boundary conditions. Ultimate aim is to see at what temperature the sand is getting. Once the sand melts, it is actually going through this constant temperature latent heat, the thermal energy storage system phenomena, and that's how you can charge and discharge at such high temperature, get a better second law efficiency thermal battery. So that was the main point with which we wanted to understand how the physics behind this melting of sand will be utilized for making an efficient thermal battery or efficient thermal storage system. These are the basic equations where you take the control volume and you employ the principle of conservation of mass, momentum, and energy using Navier-Stokes equation, and then you impose the boundary conditions and then come up with the solution or the temperature profile of that particular control volume, which you are actually making the change. So this is something where you can say the full silica, and one side you are giving certain temperature in the form of heat, and that is actually propagating, and ultimately the solid sand one side it is becoming, and eventually the entire thing becomes there. So that's how you wanted to understand. We have not yet done any practical experiment till now. It is all by doing some CFD or computational heat transfer. We are trying to understand how it is going. What we found, generally what happens, like if you are having air in this room, hot air always goes up and cold air always comes down, right? We know that, and that's how the current gets generated and we get the circulation. That's how storm happens just pre-monsoon, and when we are having the hot air from the summer, that becomes lighter and it goes up, and then the swirl or the convective currents gets generated. But in this one, there was a very peculiar behavior which we found. After the sand gets melted, the lighter one, it was going on the bottom side in comparison to that of the heavier one, which is going on the top side. So first we thought that we have done some mistake, maybe the boundary conditions were not employed correctly. So we wanted to just investigate it. What is the main reason for which this type of behavior was happening? So what we found is that here I have mentioned it. So what we found is that the melting temperature of sand, it is around 1415 degrees centigrade. And when we are speaking about the solidification temperature of the sand, it is around 1400 degrees centigrade. So solidification and melting is not happening at the same temperature. There is a certain difference in temperature, and that's how after it gets melted, it comes on the downside, because the density of the liquid sand is much higher in comparison to that of the density of the the solid sand, and that's how the convective currents were made in the opposite direction. So then it was a quite new founding, and we found that it can be utilized for designing a thermal battery utilizing silica as the phase change. So this was one thing which we appreciated. But if I'm speaking about any other inorganic salts, it happens the same way. Once it is liquid, then it becomes lighter and it goes up, and the heavier salt, solid salt will be the bottom side. So it was having a different direction of the current getting generated in comparison to that of the sand, where the density of the liquid sand is much higher in comparison to that of the density of the solid sand. And this actually helped us to design the system more efficiently, because we wanted to actually find out how this type of thermal batteries can help us to be utilized for power generation, and that we have actually designed in the lab, where we have taken solar salt. Solar salt, basically it is the nitrates of potassium and sodium, 60 and 40%, which can be utilized for storing energy at a temperature which is beyond 200 degrees centigrade. That is the range in which the solar salt can be utilized for storing. So we designed that type of thermal battery, and then we had the phase change material, which is the solar salt, being melted by a heat transfer oil. So the heat transfer oil was utilized for melting the solar salt, which is being embedded in this cylindrical cell. So we had one cold side and one hot side through which the oil was being pumped, and ultimately is the phase change material or the solar salt, which is being actually energized with the help of a winded electrical heater. But when it comes to the discharging part, by the circulation of the hot oil, whatever is stored by the winding of the electrical heaters, basically we were trying to mimic, if we can have the solar energy, how it can be mimicked by utilizing that electrical. This was a lab experiment, it was inside the lab. So just wanted the solar field by utilizing the electrical and the heat transfer oil for discharging the entire scenario. We did this study, and then we understand at which angle is better option for charging and discharging, starting from the vertical to the horizontal, starting 0 to 90. Wanted to have the parametric study at 60 degrees centigrade, then 90 degrees, and 160 and 90. So just to find out which will be the better influencing configuration when we want to have the advantage of gravity for charging. So we got very good, we got very good comparison of the computational heat transfer model, which I just discussed about the silicon, with that of the experimental setup which has been designed in the lab at IIT Delhi, and we wanted to understand what way this charging and discharging is getting influenced when we are comparing the experimental discharging of this latent heat solar salt based system, and we found that the horizontal domain melting is much faster in comparison to that of the vertical domain, by virtue of this upsurge in the natural convection or the convective current which is happening when you are having the solar salt being energized using sun and being discharged using the heat transfer oil, which is circulated through the center or the central part of the thermal battery which you are using. So the next study is again a very innovative way of understanding. If we are having the phase change material and if you are having certain stirring mechanism, the stirring mechanism, how it can help to overall enhance the charging of the phase change material, because you are again getting it exposed to the solar energy. But can an extra mechanical system helps to enhance the overall the charging time? Can it actually reduce the charging time and enhance the overall efficiency of that thermal battery? So with that in our mind, we designed this thermal energy storage system thermal battery, which was again a PCM. It was d-mannitol. D-mannitol is one of the type of sugar which is utilized for various applications of solar cooling. So the battery which we have made, it was a thermal battery of 850 kilojoule, and the overall stirrer power whichever we have utilized for stirring this phase change material, it was around 100 watt. So 100 watt of stirrer power, and the battery was having an energy of 850, and it was a small thermal battery, and the mannitol which was around 2 kg of mannitol. Just we want to understand the stirring mechanism is actually helping enhancing the charging mechanism, or it's because you see when I'm introducing stirring, it is actually power consumption. As I'm saying, 100 watt of power is required. Is that worth to use 100 watt of power to enhance the overall charging of the battery, charging of the thermal battery? That was the main point which we did this experiment. We found very good results where we found that this outermost layer of the PCM, which was not at all getting like melted so fast when we were not having the stirring mechanism, it actually started melting in a very faster rate, giving a better option of this thermal battery, having less number of hours to charge the battery at the expense of the 100 watt which we have utilized for stirring the system. So the optimization was whatever energy we have utilized for stirring the system is much lower in comparison to that of the time which is required for making the system charge. So that way the charging time was reduced, and that was giving us an advantage in terms of storing the energy, and then again that was my study. So, this is again uh, the more demonstration of how this charging and discharging is being affected when having study. And some things are giving at what RPM 100 watt stirring mechanism was being rated, and the melting time how it got reduced by around 12 milliseconds comparison to that of the mechanism when there is no stirring mechanism. So the branching happens very quickly in comparison to that of not having stirring mechanism for that thermal. So then we wanted to understand, as I'm saying that we have power, and then we have a stirring power also, which is an extra one which is there. So but you can see that with stirrer the charging efficiency actually got enhanced from say 68% to that of the 70%. So that is one advantage we wanted to have, and the total energy intake by the stirring mechanism of 100 watt stirrer is around 300 kilojoule, while the input energy which we have saved because of the reduction in the time of the charging is actually 3. So there is a delta of which we got as an advantage by utilizing this faster charging mechanism. The next one is a very big system where we had a poly generation to IIT Delhi. So visit the facility. So we have thermal battery which is utilized for space heating and probe drying, and so all those three activities, all those three poly generation activities is being backed up utilizing the thermal. And that thermal battery is actually combination of solar salt and nitrate and nitrites of sodium. So there was solar salt, of course, is having sodium, but we had also the other two, which is nitrates and nitrates. And then one more system we have introduced in this thermal energy storage system, which is the cascaded system. Cascaded system is nothing. You will be having series of phase change material which are being arranged in a way the melting point of one will be actually helping you to trigger the melting. Once the entire first chunk of salt gets melted, it will transfer the heat to the next chunk of salt. That way what happens, the overall round trip efficiency of that thermal battery get enhanced when you just uh, stack the phase change material in a way of reducing melting point of that particular thermal battery which you have used. So that way the round trip efficiency gets enhanced. So as I was saying, nitrate and nitrite, so they were actually cascaded to get this advantage of utilizing the melting point of the one to get it. the next phase of solving. So this we have utilized, and this is the whole, it's just a CAD drawing, but to come there you can see the whole system and how it is being utilized for actually space heating. And then here I have just demonstrated the space heating part, but we also have the probe drying, and we also have the cooking associated with it. And this is mainly designed for high altitude, like the project is for Lehi region where the temperature sometimes in winter goes to minus 30 centigrade. But with the help of this thermal energy storage system, you can actually make space heating possible. You can actually make possible when people are not having a conducive environment to live there. And since Leh Ladakh is one of the crucial region where we are being surrounded by other countries on that side, so this type of solution will actually help us to make the system more sustainable when it comes to utilizing this thermal energy storage system at high. We'll not go into the details of it when it goes with the thermal, but this is another part of the research which I work more on the building energy conservation. You would have heard about building management system. You would have seen Schneider, Honeywell, the PMS, where they just display the temperature, the relative of the. So basically, it helps us to cater to the energy requirement of that room, and at the same time, how much of energy is getting consumed in that, utilizing smart metering system. So that is also one area in which we work. So I wanted to just couple the thermal energy storage system for space heating and wanted to understand how the thermal comfort is being like conceptualized or envisaged when we are having the space heating using those thermal batteries. So here we have certain microclimatic data logger where we measure the driver temperature, the vector temperature, the so as to get the overall air conditioning load of that particular room in which we are sitting. So that also depends on the number of the sitting in that room, the perspiration rate at which the person is perspiring, and what sort of environment you are in, how the outside is. Is the outside as minus, or is the outside scorchy of 50%? So all those things are taken into consideration to understand the utilization of phase change material based thermal battery, which can be utilized for space heating at the higher altitude of that is one study we have done. And then gauge the thermal comfort. There are certain, we have heard about American Society of Heating, Refrigeration and Air Conditioning Engineers. So ASHRAE is a body which actually helps us to gauge the thermal comfort and the energy consumption by HVAC, heating, ventilation and air conditioning. So that also has been incorporated. So this is actually the room which is being energized using the fan coil unit, which is being heated during the month of December using the thermal energy storage system which is outside, and we wanted to see what is the temperature, what is the relative humidity in that room, so that everyone who are sitting in that room are thermal. Not good. Sorry, this is not on thermal storage directly. This is how to show the impact of thermal energy storage on the thermal. The last one is the phase change material slurry by using a double pipe heat exchanger or a piping pipe heat exchanger. Our objective was to understand the flow and the heat transfer behavior of a slurry based phase change material when it is being passed through a double pipe heat exchanger. We have done certain experiments to find, does this slurry based double pipe heat exchanger gives a better option of heat exchange in comparison to that of just a liquid based heat exchanging system. So that is how this system was designed. And here we have used micro encapsulated exchange material slurry. Just took it and then we mixed it with water. Get the slurry to different concentrations. We optimized it, and ultimately we found that which is the optimal pumping power which is required to pump the slurry a station A to station B, and to have the maximum say, optic transfer outside to the other side or to the other side. So this is the physical model in terms of the journey of so what all it is and how the heat transfer like software system. So this is the experiment setup which we set up by certain organization so that this piping pipe slurry based heat exchanger can be understood so as to have a better option on just liquid. So this is how the micro encapsulated so commercial micro encapsulated so just it actually after it manufactured it's not just great. We have our own micro encapsulated so we have utilized in the buildings. Mm, that is one thing which we have developed at IIT Delhi. This one, the first one we purchased it, got the commercially available digital material. Of course, as a routine, we have all its material characterization can find its signature in terms of how much of like the sphericity is there. Because this all actually impacts the overall transfer of the slurry which you are utilizing for transferring from the slurry side to that of the hot side. So have characteristic the micro capsule particles here seem to be smooth and spherical. And most of these particles they have a regular shape as you can see scanning certain uh, particle size variation of the someday or the size of since it is a micro encapsulated material, we have to understand what is the characteristic size of encapsulations and how floating. So these all characterizations even change the page actually like employing them for study characterizations. So another part is the estimation of the storage capabilities done using differential scanning. We wanted to understand the phase change properties of this microcapsules and find out the peak temperature, the peak enthalpy, which is changing its phase and crystallized. So this experiment is done and then see after cycles the slurry is, the microencapsulated slurry is losing its efficacy. So we run cycle and make sure see that cycle also properties the heat storage capability of the heating storage and heating capacity of that microencapsulated slurry was intact. So we were rest assured that this is a good candidate when we are trying to devising a slurry distribution. Then we made the slurry. This is a comparison of mechanical mixing, ultrasonication, and finally check the fluid slurry to mix it with the water and get to the slurry pass through one side of the mixture, the other side is the hot fluid, water. So then we have to do the heat transfer calculation. It's a very standard heat transfer parameters which we generally try to find out of this piping pipe slurry based heat exchanger. Generally for any heat exchanger, find out this non-dimensional and is the overall effect of that same has been done slurry as a part of exercise we have as a of the experiment setup which has been this yes results which has been published in the so good for the transfer as well as for the pressure. So this friction factor is more like giving the signature of the pressure drop and the Nusselt is basically the transfer. This we have specification cycle as well as cycle. So once it is ready, once it is stirred, that 100 watt which we have utilized was the penalty. So we found that penalty is a better option, enhance the overall system's cycling efficiency by reducing the charging. There also, we are using slurry and there is a pressure drop. But the pressure drop often is not that fast, but we had an advantage with the high capacity of this microencapsulated heat, high heat capacity of this microencapsulated phase more heat is absorbed and that heat is getting absorbed then what is in the same fluid gives an advantage at the cost of whatever the pressure drop is through the system. So we found that also it gives the noise to the certain so basically around 10 noise conversion. So this microencapsulated slurry based heat exchanger was not a better option. So I did not get did not obtain the required energy from and similarly as I told like that is charging also charging discharging. So this one see that there is a increase in the viscosity and the reduction in the temperature, which actually led to an increase in the temperature. So the is very positive. Here we found that larger pipe size than taken the slurry based testing. There is actually a ratio of the energy transfer and like the pressure from is actually a better option. However, this is a negative point, but that also should be highlighted. So this performance of this microencapsulated crystal is very basically gets reduced at a higher which I just showed. Thank you. If you have any questions, I can answer it. Otherwise, you can write to me and go to IIT Delhi's website and enter email address. So we have done. Actually, this is a very good question. But we have taken stirrer. It was only one. In stirrer, there are many types of stirrers, like flour based, or it can be pipe based. Yes, low, two low based, or a pair of stirrer. So that will have lot of impact on the overall mixing phenomenon. But what we have taken was a simple two low stirrer, and our idea was to see that whether this we are spending an extra 100 watt of energy. Uh, is this spending of 100 watt of energy is actually taxing on us or whether it is having an impact on fastening or making the discharging faster. If you don't have any stirrer, then it will be layer by layer the melting will happen. The outside is at a higher temperature and then eventually comes. But if you are having a stirring mechanism, it will not be happening layer wise, it will happen in one stroke. That way you will be having lesser time or the melting faster. And that faster melting, even though we are using 100 watt of power for our case plus 100 watt of power, it will actually have a better advantage as I showed around delta of energy was around 50 joules of energy which we have saved in utilizing this stirring mechanism in comparison to that of not having any stirring mechanism. But that what you are saying, you are having different configurations of study. Of course, this will be a very good study to see how and what way different configurations of stirrer will have an impact on more on the charging and discharging. Of course, it will have if we are having more lobes or even the shape of the stirrer is changing, then maybe we will be having much faster way or lesser time when we are having too low to stir. But that we have not done. It was just a beginning, but I think we should look at it.
Sir, we have discussed that energy. You cannot
Dead state.
that state
Ji,
that you cannot expect.
that
That is due to the residual entropy.
That's right. That is due to the residual entropy. For example, if you are having say water at room temperature, even though the water is I just gave two liters of water which is at room temperature, so it will have certain energy. Like if you say water liter and mass to be more or less same, so you multiply it by 4.2 and then the 30 degree centigrade. So if you multiply that, it will be the kilojoule of energy which that water is at. But you can't extract that energy because it is at 30 degrees centigrade. Once it is at an elevated temperature, then only you can extract energy from the thing. So more nearer to the dead state, thermodynamically it is a loss. More far from the dead state, thermodynamically it is a better system when you are speaking about the entropic efficiency or secondary efficiency. But the challenge is if you are at a very high temperature, how will you arrest the heat? Because at a high temperature, then more heat dissipation will. So you should have good insulation. You should have other techniques to arrest it. You can manage it, then it is comparable to that of a lithium-ion battery, where energy density is one of the like USP unique selling point for a lithium storage system. You can write it if you want.
Thank you very much, sir, for your inspiring and insightful plenary talk. Your valuable explore innovative solutions for a sustainable future. On behalf of Meerut Institute of Technology and the organizing committee of ICRIST 2026, we extend our heartfelt gratitude for your gracious presence and valuable time. Once again, please give a huge round of applause. We will now commence to the offline technical presentation sessions. Before we begin, it's my privilege to welcome our respected session chairs, Professor Dr. Suneet Shukla sir, Dr. Sayyam Sharma sir, and Ms. Shilpi Gupta ma'am. Please welcome them with a huge round of applause. May I now invite Ms. Alice Sharma, author of the paper titled Alice